Welcome to Unit 5, Applications of Integration, Calculus AB. Part 1. How do you calculate the area between two curves with respect to x and y? First, identify the functions. Let's say that f of x is the top function, meaning it has the larger y value across the interval. And let's say that g of x is the bottom function, meaning it has the smaller y value across the interval. Second, find the points of intersection where f of x equals g of x. These are the x values of the interval a and b. Lastly, set up the integral from a to b of f of x minus g of x dx. This will give you the area between the curves. When evaluating the area between the curves of a function with respect to x, it is always top minus bottom. For if you want to evaluate the area with respect to y, replace all the x's with y and replace the interval from a to b with y values c to d. Here, instead of top minus bottom, it's right minus left. Part 2. How do you determine the bounds of the integral expression if they are not given? First, set the two functions equal to each other. Then solve for the variable with respect to the correct variable according to the problem. The solutions are the bounds. With respect to x, f of x equals g of x, and bounds are a and b. With respect to y, f of y equals g of y, and bounds are c and d. Part 3. How do you determine which graph is on top or bottom, or left or right, if the graph is not given? With respect to x, choose a value x between bounds. Plug that x into both functions. Compare the y values. A higher y value indicates the top function. A lower y value indicates the bottom function. With respect to y, choose a value y between bounds. Plug that y value into both functions. Compare the x values. A higher x value indicates the right function. A lower x value indicates the left function. Part 4. What should you do if the top or bottom function or left or right function switches at some point within the interval? First, find all points of intersection by setting the two functions equal to each other. Then determine which function is on top in each subinterval by testing values between the points of intersection. Lastly, split the integral at the intersection points and set up separate integrals for each part with the correct top minus bottom or right minus left order. Part 5. How do you know when to use the disk method or washer method? Use the disk method when the solid being evaluated has no hole in the middle, or when the region is flush against the axis of rotation. The basic formula for the disk method is volume equals pi times the integral from a to b of the radius squared with respect to x. Use the washer method when the solid has a hole in the middle, or when you're revolving around a region bounded by two curves. The basic formula for the washer method is volume equals pi times the integral from a to b of the outer radius squared minus the inner radius squared with respect to x. Part 6. What are the formulas for the disk and washer methods with vertical and horizontal axes of revolution? For the disk method, the formulas are as follows. For a function with a horizontal axis of revolution, the formula is volume equals pi times the integral from a to b of the radius of x squared, dx. For a function with a vertical axis of revolution, the formula is volume equals pi times the integral from c to d of the radius of y squared dy. For the washer method, the formulas are as follows. For a function with a horizontal axis of revolution, the formula is volume equals pi times the integral from a to b of the outer radius of x squared minus the inner radius of x squared dx. For a function with a vertical axis of revolution, the formula is volume equals pi times the integral from c to d of the outer radius of y squared minus the inner radius of y squared dy. Part 7. How do you find the radius or radii for the disk and washer methods? The general rule for finding the radius or radii for these methods is that the radius is always the distance from the axis of rotation to the function or curve, perpendicular to the axis. Part 8. What is the formula for volume of a solid with square cross-sections? The formula is volume equals the integral from a to b of the side length squared dx. The side length is equal to the length of the segment between the top and bottom curves at each x. The side is the base of the square, so squaring it gives the area of each cross-section. Part 9. What is the formula for the volume of a solid with rectangular cross-sections? The formula is volume equals the integral from a to b of the base of x times the height of x dx. Base is the length of the segment between the two bounding curves. Height is the fixed or varying height perpendicular to the base. Part 10. What is the formula for the volume of a solid with equilateral triangle cross-sections? The formula is volume equals the integral from a to b of square root 3/4 times base squared dx, where the area of an equilateral triangle is square root 3/4 times the side length squared. Part 11. What is the formula for the volume of a solid with isosceles right triangle cross-sections? Volume equals integral from a to b of 1/2 times the base of x squared dx, where the area of an isosceles right triangle is equal to 1/2 times the base of x squared. Part 12. What is the formula for the volume of a solid with semicircle cross-sections? The formula is volume equals pi over 8 of the integral from a to b of the base of x squared dx, where the area of a semicircle is 1/2 pi r squared. Part 13. What are the bounds, equation form, length and variable of integration for cross-sections perpendicular to the x and y axes? For the x-axis, the bounds are the x limits of the region, from a to b. For the y-axis, the bounds are the y limits of the region, from c to d. The equation form depends on the cross-sections. For example, square semicircles. It depends on the cross-sections. Those formulas were mentioned in previous parts. Length is the distance perpendicular to the axis of revolution. The variable of integration is usually x for cross-sections perpendicular to the x-axis. It's usually y for cross-sections perpendicular to the y-axis. And that wraps up Unit 5, Applications of Integration, and with it, the entire Calculus AB review series. We covered everything from areas between curves to volumes of solids using disks, washers and cross-sections, with all the key formulas, setup strategies and integration techniques you'll need for the AP exam. If this series helped you, make sure to like the video and subscribe for more animated explanations, review content and tips for crushing calculus. Thanks for sticking with me through all the units, and I'll see you in the next series.